Hello, ma'am. Can you give access to the chat so that students or participants can ask questions during the presentation? Because right now I'm seeing that the chat is disabled for everyone.
Hello, good evening, sir.
Yeah, good evening, ma'am. Yeah.
Sir.
So I was saying that if you can give access to chat for everyone so that they can ask some questions or anything in the chat also during the lecture. Because
Okay,
right
okay.
now the chat is not enabled.
You can, so can you see my message, sir? I sent one message in chat box.
Nothing. We can't.
Nothing.
I at least I
Oh,
can't see any message. If anyone else can
oh,
see, maybe they can confirm.
okay. So that is in blue color. So I will tell, sir. Okay.
Okay, okay, sure.
So, good evening to all of you. Good evening, sir. Avin, sir.
Yes, ma'am. Good evening.
Good evening, sir. So, today we are move on to the third day faculty development program. So, today, sir will deliver the lecture on naive Bayes and decision trees. So, dear participants, the attendance is compulsory on all days. You will require to present at least 80% of the session time, and you can post your questions in question, and otherwise we can raise your questions in chat box also. So, sir, you can start the session. I mean, sir.
Yeah, sure, ma'am.
Okay.
Yeah, good evening, everyone, and welcome to the day 3 on foundations of machine learning and deep learning. A brief introduction. My name is Aveen Dayal, and I'm a PhD scholar at the Artificial Intelligence Department at IIT Hyderabad. So, in the last two lectures, in the first lecture, we discussed briefly about what machine learning is and a little bit about the different types of machine learnings. Uh, I request everyone to please mute yourselves. If there is any question, only please unmute. Yeah, thank you. So we've discussed about a little bit about the different settings, and then like supervised learning, unsupervised learning, and then we talked about the evaluation pipelines, that is the training set, validation set, and we also discussed about evaluation metrics like accuracy, precision, recall, and we saw a simple algorithm of k-nearest neighbors. And yesterday you've discussed your first machine learning algorithm, logistic regression. So logistic regression is sometimes also called as the basic machine learning algorithm because anyone who starts with machine learning comes across logistic regression. So it's a very simple and very easy to implement, but make sure you understood that correctly because the entire concept of logistic regression is what will be used in today's neural networks. So if you understood logistic regression correctly about how it is working, then neural networks understanding will become very easy. So that we will discuss when we come to that chapter. Today we will move on from logistic regression and talk about two more important algorithms, naive Bayes and decision trees. Both of them are very interesting, and I hope you enjoyed today's algorithms also. So this is a small recap. This is what your typical data set looks like for classification. The entire Excel sheet or CSV data is your input data X. Your attributes are the features, which is the first four columns. Today we will be working on this data set itself during the code implementation. So this is a popular data set called Iris data set. I'll show you the images and how it looks like. So we have four features in this data set, sepal length, sepal width, petal length, and petal width. We'll discuss what those are. And we have three classes on this data set, Verisocolor, Virginica, and Setosa. So I just wanted to give you a feel about how the data set, and remember this when we are discussing today's algorithm. So as usual, this is what a classification looks like, a classification task. All you need to do is find a straight line that separates these two classes, or find multiple straight lines or a complex line that will separate all these three classes. So that is the goal of any classification algorithm. So we also call this line the discriminating line or the discriminator. So a small preview about the evaluation itself. So this is a standard evaluation which we discussed first, where you divide your entire data set into train part and the test part, and you fit your or train your model on the train part, and then finally you evaluate on the test part. How do you evaluate? You calculate, you have a scoring metric which tells how far or how close you are from the true labels. So that is what your performance metric is. Okay, so before moving on to naive Bayes, so naive Bayes is derived from the popular probability theorem, Bayes theorem. So that again deals with a little bit of probability. So so that everyone is on the same page, I wanted to discuss briefly 1-2 slides about probability and conditional probability, and then we can move into the actual algorithm itself. So probability, like I think everyone knows, a standard definition is probability measures how likely an event is to occur, and the value of probability lies between 0 and 1, where 0 means the event cannot happen and 1 means it will most likely or definitely happen. Simple example is your email spam emails. So you will be receiving, let's say, 100 emails in a week, and 20 emails of those are spam. So what is the probability that you receive a spam email? It is nothing but 20 divided by 100, which is 0.2 or 20%. So this is a very simple example of a probability. Now let's move to something called as conditional probability, which says that what is the probability of a certain event given that another event has occurred. So as you can see, the notation is probability of A given B. B is an event that has happened. So what is the probability? Now A is happening given that B has happened. So let's go back to the previous example of emails itself. So if you notice that out of the 20 spam emails, 10 emails you receive on weekends. Okay, so now your conditional probability of receiving a spam emails you receive over the weekend, which is 30, and the number of spam emails you receive on the weekend, 10. So it is nothing but 10 divided by 30, which is 1 by 3 or 33.3%. So this is a little bit conditioning because we are looking at now ki I just want to see on the weekends what is the probability of getting a spam. Previously, we are just asking for what is the probability of getting a spam email throughout the week. So this is a slight difference between probability and conditional probability. Okay. So now let's go to the main algorithm itself, which is the naive Bayes algorithm. So naive Bayes algorithm basically looks at, imagine you're a detective. Yeah, sorry for that. Yeah, so imagine you're a detective. So everyone knows what the detective does. He basically tries to gather different clues and then he comes to a conclusion that a particular person is a suspect. So that is what a detective's basic job is. So naive Bayes can be clearly understood like what a detective works like. So let's go step by step. The first step, what does a detective do, or what you should do, is gather clues. In our case, what are these clues? These are nothing but features of the data. So in the second step, you need to understand what is the usual. So what is a trend that actually happens? We call it calculating prior probability. Don't worry, we'll discuss it with more concrete examples, but these are the actual terms which you see in the brackets. The left side are more like understanding what the terms mean. Then third is you're weighing each clue against each other. So that is what we call as calculating likelihood. So this could be like, imagine there are two clues, a person maybe going in a rain, or person who's took a cab instead of walking in the rain. So you weigh against which are the two possible likelihoods across these two events. So that is what you calculate the likelihood. The fourth is an important point. We ignore complex relationships. This is where the naivety comes from. So naivety means ignorance or simplicity. So naive Bayes algorithm is also called as a simple implementation of the Bayes theorem. It's sometimes also funnily people call it the dumb version of the Bayes theorem. We'll see why it is called the simple or naive version of the Bayes theorem in the next slides. But remember that you're ignoring complex relationships. That is why this algorithm is called as naive Bayes algorithm. Then fifth step is where you actually calculate the posterior probability, which is called as where you make a call. Okay, you collected all the clues, you weighted each clue, and now you have to finally make a call. What is the most possible likelihood that has happened, or posterior probability that has happened? And finally, your decision time is you pick the particular person as a suspect. So this is what 6 simple steps in naive Bayes algorithm does. Now let's look at it. Okay, before that, let's look at the equation itself. So this is what a Bayes theorem looks like. So on the first equation which you see, the left thing is leftmost term is called as the posterior probability. It is nothing but probability of a given class C, probability of a class C given an input X. Your X is your input data, C is your class. So posterior probability is probability of class C given your input X. That is what we want, right? So when you're doing test time also, what are we doing during test time? You're given a test sample. Now you need to predict which class that particular test sample belongs to. That is what the posterior probability is. Now let's come to the right side and let's look term by term. The first term is the likelihood. Likelihood, like I said, it is calculating or weighing each attribute or each feature against each other. So what does in terms of probability it means? Probability of the input X given a particular class. So this is called as likelihood. Now let's go to the second term in the numerator, prior probability. Like I said, prior probability is nothing but what is the usual trend that happens. So in this case, it will be what is the probability of the class C itself in the entire data set. So this is your prior probability. Then your denominator is your predictor prior probability, which is probability of X itself. So in our case, usually we ignore the denominator because it's hard to calculate the entire input space probability. Like I said, we don't have the entire input that is universally available. So it's a little bit hard and we can sufficiently ignore the denominator. So we only worry about the first two terms in the numerator. You multiply them and then you get your posterior probability, which is directly proportional. Now, where does naivety comes or the simplicity comes? If you can see in the last equation, usually your X, like I said, your input data has multiple features, right? X1, X2, X3, X4. Ideally, when you expand this likelihood, it should be probability of X1 given C, then it will be probability of X2 given C and X1, and then it will be probability of X3 given C, X1, X2. So it will be a big complex equation. But naive Bayes says that let's ignore that complex part and let's simply expand independently. So if you see on the bottom here, X1 and X2 are independent. If they were dependent, you will see in when you're expanding X2, you will see X1 term also after C. But since you don't see it, it means that they're independent events. So this is your naivety or ignoring the complex part. So the likelihood or the posterior is nothing but probability of all these likelihoods, X1 given C, X2 given C, so and so up to nth feature Xn given C into the class prior probability. So I hope this is clear and the naivety in naive Bayes is clear. Any questions, please drop your questions in the Q&A forum. I'm looking at it from another screen so I can answer it. You don't have to wait till the end of the session. Okay, so if this is clear, let's move on and calculate some values, or let's look at a more day-to-day example before that. So in the email example itself, so let's go step by step and see how naive Bayes solves that email example. So each word in your email is a feature. So now your feature is nothing but your entire word in your email, whichever you get. Understanding the usual is calculating the prior probability. In general, how many emails are spam emails? Like I said, you get 80 emails as non-spam emails. So 80% of the times the email you get is not a spam. So that is your calculating the prior probability. Now you have to calculate likelihood. So how do you do that? If, for example, the word free appears in 5 out of the 20 spam emails, then you see that this particular feature is the probability of this feature occurring for a spam email is 5 by 20, which is 0.25. So this is just one likelihood, like you can say, this is just like probability of X1 given C. Similarly, you have to calculate for all the words in the email, probability of X2, second word, third word, up to the nth word. So that's how you keep on calculating for all the n words. And we are already using the naive assumption where you simply multiply all of these probabilities which you calculated in step 3 with each other. And then posterior probability is nothing but multiplying this likelihood with the prior probability. You can ignore the denominator, like I said. And then finally, you make a decision based on this posterior probability, whether this particular email is a spam or not. Now, if you look at it in a more, yes, is there a question? Okay, so if there are no questions, let's move on. Let's look at it in a more disease prediction. So naive Bayes has been popularly used up until recent times, till 2000 at least. It was popularly used for two things. One is a spam email detection, which even till date a version of it is used in your popular Gmail accounts. I think even other email accounts use them, but in Gmail it was very popular, naive Bayes. And another thing was disease prediction. So people still calculate for some cases using naive Bayes for certain disease prediction. Of course, you have much more sophisticated algorithms, but naive Bayes still is very a powerful algorithm. Okay, let's go at the disease prediction. So there is, let's say you have a disease called gigantism, and there are 3 features for that particular disease. What are the 3 features for the input? Your tall stature, which is basically how tall that person is, and your enlarged hands and feet, which you call it as enlarged, and then your excessive sweating. If you sweat excessively, it's this particular feature. So you have 3 features which you look at to decide whether a person has this disease, gigantism or not. Okay, first you gather your features, that is collect your data. Second, you're understanding the prior probability. It means that based on the historical data which you have, obviously every disease has some history, right? Based on this entire historical data, let's say you identify that 2% of this people 2% of people in general have the disease. So what is the prior probability that gigantism is exists as a disease is 0.02, and probability that a person will not have prior probability of not a gigantism is 0.98. So this is how you calculate two prior probabilities. Next, you calculate your likelihood. So how do you calculate likelihood? First is probability of tall given a particular gigantism case. Next, you calculate the probability of enlarged given a gigantism disease person. Then you calculate the probability of sweating given a particular person has gigantism disease. Let's say for now you got these values 0. 0.9, 0. 0.95, 0.6. Since it's naive base, naive assumption, you multiply all these three values along with your 0.02. So that is what making the call is, where you multiply all these three likelihoods along with your prior probability. Similarly, you repeat for not the gigantism class also. So now you have two posterior probabilities. One posterior probability is, sorry, it should be opposite actually. It should be probability of gigantism given all the x, not this value. I'll change it while sending you the slides. So it's a probability of gigantism given the input. Similarly, calculate for probability of not gigantism given the inputs. So you have two values now, posterior probabilities, and it's simple. Whichever has the higher posterior probability, you pick that in your decision. It's very simple once you have the posterior probability for the two classes. Okay, so I hope this is also clear. So now let's look at how the decision boundaries are usually formed with this what do you say, naive base. So previously, yesterday when you saw logistic regression, you saw a simple linear classifier being formed. So a difference between a linear classifier and a non-linear classifier, like the name suggests, when your decision boundary is something which is not a straight line, it is a non-linear classifier algorithm. Whereas if your classifiers or if your algorithm always gives only linear decision boundaries, it is called as a linear classifier. Naive Bayes is good and better than logistic regression because of its capacity to form these non-linear decision boundaries. So that is why people use naive Bayes for more complex tasks compared to logistic regression, because it was able to form this nice parabolic curve which separates these two classes, red class and the blue class. Okay. Now let's actually solve a problem. So I've been talking a lot about these steps and everything. So let's actually get into it and solve a problem. So naive Bayes usually starts, let me just show, yeah. So naive Bayes first requires a test example. So naive Bayes doesn't really do much on during the training time. It basically starts working, it just collects some data during the training time, but the actual implementation or the working of the algorithm happens when you're given a test example. So let's say this is the test example you're given. Just a second, the pen is not working. Yeah. So let's say this is the test example that you're given. What is my test example saying? I have, first let's look at the data itself, sorry. What is my entire data? I have a bunch of features, name, these are different attributes with of animals, give birth, whether it can fly, whether it can live in water, whether it can have legs. And then you classify based on these input features, whether that particular animal is a mammal or non-mammal. So this is a simple binary classification. There are two classes where you can classify it as a mammal or non-mammal. So what are the important features in this? Obviously, the name is not important because name is a unique value for every animal, right? So you really don't care, you don't get any information from this column name, so you ignore name. What are your other important features? These four. Give birth is basically whether that animal can give birth, or second is can it fly, can it live in water, can it have legs. So these are the four important features. So now when your test example comes, this is how your bottom is a test example. You are given the values for the four input features. It, like for example, in this particular case, you're given give birth is yes, can fly no, live in water yes, have legs no. Given these four values for these four features, what is my class, whether it's a mammal or not? Now you are given this test example and now you backtrack and look at it. So how do we look at it? First is we have to write down these three variables. A is for attributes, M is for mammals, N is for non-mammals. So once you collect the data, what is the second step? Calculating the prior probability. So prior probability is calculated. No, sorry. Prior probability is calculated is in probability of M and probability of N. Probability of M is 7 by 20. Probability of N, which is non-mammal, is 13 by 20. How is it? It's simple. Just look at the table, right? What are number of mammals? Total there are 20 rows. In that, mammals are 7. This is 1, 2, 3, 4, 5, 6, 7. So there are 7 mammals out of these 20. So the probability is 7 by 20. That is what you see over here. Similarly, for non-mammals, it is just 1 minus mammals, which is 13 by 20. So now once you calculate a prior probability, next is weighing the clues or calculating the likelihood. So let's look at the likelihood. For the first one, we look at when the class is mammal. So you only focus on rows which are mammal classes. So you look at only these 7 rows which are mammal classes and ignore the other rows. Now inside the mammal classes, for the first attribute, what should I focus on? Value. It is the test example says yes. So I only focus on the values which are yes. So what is the likelihood that my given birth is yes, that my given birth has a value yes, given it's a class mammal? Just see how many yeses are in mammals. This is 1, this is 2. I hope there's a pen is working. That's okay. Let's go this way. This is 1, this is 2, this is 3. Then sorry, this is 4, this is 5. We ignored this because it's a no attribute, and this is 6. So total you have 6 yeses and total number of mammals are 7. So that is how you get the first term, 6 divided by 7. Now similarly, let's look at the second attribute where the value is no, and you'll have to again look at the mammal class, the 7 rows where the value is no. What are those? Let's take a different color. 1, 2, 3, 4, 5, and 6. So again, you have 6 out of the 7 mammals. So 6 by 7. Similarly, we'll go for the third feature, which is live in water, and the value is yes. So use a different color. First one is not true because it's saying no, but we want yes. Second one is true. Third one, again, we're ignoring because it is saying no, while we need yes. Fourth also we're ignoring. Then we again have third value. So yeah, we have only 2 values, which are live in water yes and for a mammal class. So that is why your third term is 2 by 7. I hope you all are following. Any questions, just drop in the Q&A forum. And then finally come to the fourth column, have legs, no. Same we'll go by fourth column for mammals. So here no is here, here, and no is here. There are only 2 values out of 7, hence the term 2 by 7. So now we are assuming the naive assumption, right? And what does it say? It just says multiply all of these features with each other. So 6 into 6 into 2 into 2 divided by 7 to the power 4, which is approximately 0.06. And similarly, now you do for non-mammal class also. You calculate the likelihood for non-mammal class for all the attributes. The same process what we just followed. Instead of looking at mammal rows, look at non-mammal rows. You will get these values, which is approximately 0.004. Now we will calculate the posterior probability. What is the posterior probability? It's nothing but likelihood into prior probability. We are ignoring the denominator. So it is nothing but 0.06 into 7 by 20, which is roughly 0.021. Similarly, for non-mammal, the posterior probability is 0.004 into 13 by 20, which is 0.0027. So it's very clear once you calculate the posterior probabilities, which one is greater? Obviously, mammal is greater. So hence, we can deduce that this particular test example belongs to mammal class. So this is how naive Bayes works. So any doubts or anything that is unclear in the entire process, please let me know, or you can unmute and also ask. Okay, great. So if this is clear, then let's move ahead. So this is how naive Bayes works. And there are variations to naive Bayes also, because if you see, there are two variations called as Gaussian naive Bayes and categorical naive Bayes. What is the difference? It depends upon your attributes, whether it's a continuous attribute or discrete attribute. So if you look at these attributes, right, all of them are discrete. It's a yes or no, which is discrete, three values still discrete, again discrete. Since all of them are discrete, you're using a categorical naive Bayes, which you calculated like we did. But if your values, attribute values, were continuous, then what would you do? You can't calculate like we did, right? Look at mammal class, look at the value yes or no, because it could be any real value. It could not fall also in this entire continuous space, the test example feature value. How do you deal with that? That is where you use Gaussian distribution. So Gaussian distribution is also called as a normal distribution. Standard normal distribution is Gaussian with a mean 1 and deviation, a mean 0 and deviation 1. So this is the equation in the red box which you see. This is the equation of a Gaussian distribution or a normal distribution, and the distribution usually looks like this. These bell curves we call it. So standard deviation is this width of the bell curve. Mean is this point where it is peaking. Like for example, I think everyone is aware, but still, yeah. So this is your mean. This is your standard deviation. So based on Gaussian distribution just needs two values to define this equation, f of x. What are the two values? Mu, which is your mean, sigma, which is your standard deviation. So if you know these two values, you can define your Gaussian distribution. So now let's look at a simple data where your status or class is whether you have a cancer or not, cancer or healthy. These are the two classes, and your attributes are in continuous space. So what do you do in that case to calculate the likelihood? First, we'll look at the cancer class, and you calculate the mean of all these values and the standard deviation. So that is possible. Mean is nothing but total sum of all the values divided by total number of values. Standard deviation has a simple another formula which is also simple to calculate. So once you get that, you know what is the distribution of your cancer class for this particular feature, which is your orange color. Similarly, for the healthy class, you calculate the mean and standard deviation. You fit in this particular f of x value in this f of x equation, and then you get this distribution for the healthy class. So once you get these two distributions, then you can follow it for all the other values, other continuous values which have. Then you do the same thing, multiply the probabilities, because now you have your distribution, right? So whatever your test sample will ask for, if this is my value, you know the probability of that value because you know the distribution itself of that particular Gaussian distribution. So then you can easily calculate probabilities or likelihoods, multiply it with prior probabilities, and then you can calculate a posterior probability. Okay, is this clear? Any doubts in this continuous space?
Can you please repeat this? Gaussian
Yes.
probability.
Sure. So in this if your features are continuous, then first look at the cancer class, or in class 1, we calculate the mean of all the values, that is your mu value, and then you calculate standard deviation using the standard formula for standard deviation or variance. Variance is nothing but the square root of deviation. Variance is nothing but the square of the deviation, square root. And then once you get these two values, you get f of x value. So now, for example, during my test time, if I say that this is PSA value. So during my test time, if I say PSA has a value of 1.3, okay, this 1.3 is nowhere in your input data, right? If you look at this 1.3 is nowhere in the input data. So, but I can calculate the probability now because I know what is the f of x equation for cancer. I know what is f of cancer because I knew what is mu of cancer and what is mu of cancer and what is the sigma of cancer. Since I know these two values, I know f, and since I know f, I can calculate the probability of this particular 1.3. 1.3, you basically input it as x over here. This x where you see, you put 1.3 and you calculate the value. So similarly, that will give you the likelihood for the PSA value for cancer class. So that will give you this likelihood, probability PSA 1.3 given cancer class. Similarly, you get likelihood of PSA 1.3 for healthy class, follow the same process, and then you multiply the first one with their prior probability, similarly second one with their own prior probability, and then you compare which one is bigger. That will be your final answer, whether the particular test example is cancer patient or a healthy patient. Is this clear? I'm sorry, I don't know who asked the question. Is this clear now?
Yes, yes, sir. Yes, sir. Thank you.
Yeah. Okay, so this is it for naive Bayes. So Gaussian naive Bayes is more popular, obvious reasons, because in real world you see more continuous data, you don't see discrete. Discrete I've explained, and everyone actually starts with discrete because it's easier to understand how it works. Okay, so let's move to our second algorithm. So if everything is clear, we'll discuss code walkthroughs, all of them together at the end. But let's move on to the decision tree. So decision tree is again a very intuitive algorithm and very simple algorithm. So what does a decision tree say? I think you all must have played this game with your friends called 20 questions. So if you haven't, this is the game. So you think of an animal, and then you ask your friend, you tell your friend that you have 20 questions to ask me 20 different questions, and within those 20 questions, you should guess what animal I'm thinking. So that's a very simple game which we all used to play. So the decision tree literally works in the same way. You start off at a root node. You ask a bunch of different questions based on your features, the input features which you have, right? You ask a bunch of different questions, and then you split the tree into multiple branches. So based on your attribute value, if it's yes, you go to the left side. If it's no, you come to the right. Similarly, on this particular node, you again ask questions, and then based on those values, you expand the tree further. So it's a recursive kind of a algorithm. Keep on asking questions at every level of the tree, and that is when you finally reach the leaf nodes, which will tell you which class that particular input example or test example belongs to. So it's also called as the inverted tree, because initially as a tree, the roots are on the bottom, the leaves are on the top. But for decision tree, the root is on the top, the leaves are on the bottom. So it's an inversion of your actual real world tree. So like I said, the algorithm is very simple. Start at the root, ask a bunch of questions at every level. Now the trick is, or the main idea of decision tree comes in finding the best question. What is that best question to ask at every level? So there is a metric which is based on entropy, which we'll discuss in the coming slides. But that is the main, gist of decision trees. And then you keep on repeating the process, and then finally you generate your leaf nodes, reach your decision, and make predictions. So let's start off with a very simple example. Let's look at this simple example where you have 4 features. It's basically weather related features. One is outlook, whether it's a rainy weather, overcast weather. Overcast is kind of like cloudy kind of thing. Then, or whether it's a sunny weather. Then you also have temperature, whether it's hot, mild, cold. Then you have humidity, high, normal. These are the 2 values. Then windy, whether it's windy, true, whether it's not windy, false. And then based on these input features, which are also called as predictors, so it's a new term again. Make sure that you remember all these terms: predictors, attributes, features. These are all the same term. Based on these 4 predictors, you have to make a decision whether to play golf or not. That is a target variable. So how does a typical decision tree looks like, which is you can see on the right side. So you start off at the top level root. So I'll tell you how to pick which attribute at the top, and at every level how to pick an attribute. There is a certain metric, like I said, finding the best question. So let's say I picked outlook to be the best question to ask at the root. Then what are the 3 different values possible for outlook? Sunny, overcast, rainy. And now you go to this branch which are sunny. So it means nothing but you look at, let's look at that. So when I say sunny, so what happens? Then you go to your outlook column, this column, and then you look at all the columns which are sunny. So you look at all the rows which are sunny. So you look at these 5 rows. Now you focus only on these 5 rows at this particular point. And now for these 5 rows, again you ask questions for these 4 columns. So what are the questions? You can ask based on these 3 columns: temperature, humidity, windy. And let's say the best question to ask at this point is windy. So let's look at here, it's windy. So now out of these 5 rows, you again have windy and split it into 2 values, false and true. Now if at this point, what are the rows you're looking at which are sunny and false? It means that you look at 1, 2, and 3. That's it. You just look at 3 values. And for these 3 values, all of them are yes, 1, 2, and 3. So that is why you end up at the class yes. So it's good to play golf when it is outlook is sunny and the wind is false. So it's good to play golf. Similarly, you expand the tree for other particular branches. So, but this is the basic idea of how decision tree expands. Now, I made an assumption, right? Identifying the best question, that we will see how to do that. So this is just another simple example. I'll just quickly go through because I think you all understood by now what it is. So you start at the, let's assume you are working in a bank and you have to decide whether to approve a loan for a customer or not. Like usual, you start off at the root of the decision tree. You ask a bunch of questions like what is the applicant's income, annual income for a year and all. So let's say you identify the best question and then you keep on repeating the process until you create those leaf nodes, and then you make the predictions based on this entire tree. So it's a simple example. You can always look at it on your own time. So these are some terminologies for decision trees. The first one is root node. All the nodes which are not the terminating nodes or leaf nodes are called internal nodes, and each level is called as layer 1, layer 2, layer 3. So these are the standard definition for any trees, right? Tree data structure. You follow the same notations over here also. Okay, so now let's move on to the metric. How do you decide which is the best question? Before that, let's look at something called as impurity or entropy. I'm assuming most of you are familiar, but for people who are not, let's look at it in a more intuitive way. Entropy defines, or impurity is nothing but when your sample which you pick is of mixed classes. So for example, on the leftmost side, the sample which you picked, there are red classes and also blue classes. So with compared to the blue classes, it's very impure. Whereas if to make it less impure, you have more blue classes in the middle. To make it completely pure with respect to blue classes, it's all blue classes. So as you can see, impurity is nothing but having more and more samples from the opposite class in your sample, in your subset. So the least is when none of the other classes are there in your sample. All of them are belonging to one particular class. Okay. Now, how do you quantify this impurity? That is how we use entropy. Entropy is closely related with probability distribution. So let's look at these 3 probability distributions, which are discrete PMFs, probability mass functions. So on the left side, there are 4 possible values for this probability distribution, and each of the vertical x-axis defines what is the probability of it. So in the first leftmost graph, what you see is that the class 1 has the highest probability, whereas all the other classes have very low probability. So this particular sample is called very pure because when you infer or when you sample from this distribution, most of the time you are getting only from class 1 because that has the highest probability. So this is a very pure, closer to pure distribution or pure sample which you look in the previous, right? Because all of the times what you get is one class only, class 1 which is. Now let's look at the second probability distribution. Here there are 2 classes which have equal amount of probability. Other 2 classes have low probability compared to the first 1 and 3. So here there is definitely impurity, but impurity is relatively less compared to the final distribution where all of the 4 classes are equally probable. In this case, your sample, when you sample from this distribution, you will be getting something like this, equal probabilities of all the classes. So it's a very impure sample. So entropy is nothing but the measure of impurity. So on the right side, if you look at it, entropy of the last graph, which is the most impure, has the highest entropy, green color. Entropy of the middle one has less impurity compared to the third one, so a little bit less entropy. And the first one has the least impurity, so it has the least entropy. So this is how entropy is inversely proportional to the not inversely, entropy and probability are correlated with each other. Okay, so but how do you use this in your decision trees? That is where the trick lies. So before that, let's go step by step. Let's first look at the entropy formula, which is on this equation, which I'm pointing out. This is the equation. Entropy formula is minus of the probability of that particular example into the log of the probability of that particular example. In our case, It is nothing but probability of for each class how many samples are there, right? That probability into the log of that other probability. In our case there are two classes, playing golf, yes or no. So c is just two values, I is equals to 1 to c. We sum over probability of playing golf into log of playing probability of playing golf minus the probability of playing golf into the log of probability of playing not playing golf. I'm sorry if I messed up that one. Let me just write it down. So this will be nothing but minus p, I'm putting y as playing for golf, into log of playing for golf minus p into not playing golf into log of not playing golf. Okay. So how do you first calculate the entropy of the play golf itself? So first let's look at how many samples were playing golf. 9 were saying yes to play golf, and no were saying not to play golf. 5 were saying not to play golf. And if you want to calculate, it is nothing but the entropy of 0.5 and 9. What is the entropy of 5 and 9? This notation means, let's look at what this notation means. This notation means nothing but you first calculate, these are the two possible classes, right? No classes and yes classes. So you first calculate the probability for no class. What is the probability of no class? It is 5 by 14. Similarly, probability of a yes class is 9 by 14. So that's how you get these values, 0.36 and 0.64. So then it's just straightforward input in the formula, 0.36 into log of 0.36, 0.64 into log of 0.64. So the entropy of playing golf is 0.94. So what does this mean? That when you originally receive your data set, this much amount of impurity is there, 0.94, which is a very high value because entropy usually goes from 0 to 1. So your initial data has high impurity, which is also sensible because you're almost having equal 9 and 5, right? 9:5 ratio. Okay, so now let's look at how do you pick the best question. That is this part. Let me do it in another color. So how to pick the best question is this particular equation. So I'll explain what it means. Your T over here is your previous parent node here, because there's the decision tree, like I said, you always have a parent and then you have bunch of options for the child. Which particular child should you pick out of these 4? That is your goal over here. So the T over here is your parent. The X is which of these 4 should you pick? Which of these 4 values should you pick? So one by one you calculate for all the 4 values, and then you use this formula for gain. Then you use this formula for gain, which tells you which particular value out of all these 4 values, entropy T minus entropy T minus X, then based on whichever is having higher gain, you pick that particular value. Let's not worry about what gain is. Let's first go back to the second equation. Let's first calculate the entropy for a particular attribute X. Let's say I'm taking one example. You can do it for all the examples. Let's say I pick the example outlook. What are the values for outlook? Sunny, overcast, rainy. So, and for sunny, how many said yes? 3 said yes, 2 said no. If it's a sunny, 3 said yes, golf, no to golf. Similarly, for overcast, there were 4 rows which said yes to golf. There were 0 rows which said no to golf. If it's rainy, there are 2 which said yes, and there are 3 which said no. Okay. So now you just calculate first the sum of these, which is 5, 4, 5. The total of all these is 14. Now you just calculate the entropy of this particular attribute. So how do you do that? If you expand this equation, it is probability of sunny into the entropy of 3 and 2. I said entropy, look at this formula. Entropy of 3 and 2 is nothing but first calculate the probability of 3 divided by 5, then probability of 2 divided by 5, and then you multiply with this equation which you just did in the previous thing. Similarly, for overcast, probability of overcast into the entropy of 4 and 0, yes and no. Similarly, probability of rainy into the entropy of 2 and 3. So then you sum all these 3 together, which is your final entropy value for this particular output. So what it means is, let me use a different color. Okay. So what it means is, if my root node had an entropy, what was my entropy? 0.9. If I pick Outlook, uh, if I pick Outlook over here, my entropy will be 0.693. So original data set had this much impurity. If I split this original data set based on the Outlook, which is three values, right? My impurity on the whole reduces to 0.69. So we are making it less impure, which is a good thing. That is what we want. And then how do you measure this? It is nothing but subtraction of 0.9 and 0.63. That is what gain tells. So gain is nothing but subtracting your parent entropy with your current attributes entropy. You do this for all your columns or attributes, and then you pick the one which has the highest gain. And that means that that particular attribute, when you pick in this level, the sample will get very much pure in the next level. So the goal of decision tree is to reduce the impurity across the different layers. That's how you come to a decision. So let me quickly pause. I know there's a lot of math and all that went, calculations. Any questions or anything that you want me to repeat? Okay, great. If this is clear, let's look at a very simple example to boil down to what this impurity concept is. So let's look at this particular simple animals example. You have a bunch of different animals. Obviously, in the topmost, your impurity is high. Why? Because you have three giraffes, you have two elephants, you have two tigers, and one monkey. So you have a lot of impurity. Now, like I said, decision tree's goal is to pick a question or pick an attribute when whose particular division based on that attribute or question will make the sample less impure. So if you pick color is yellow, now based on that you split your all the animals. Giraffes and tigers come on the left side, elephant and monkey comes on the right side. So obviously entropy is a little bit less compared to the overall entropy over here. Now based on again the height, you make the sample even more impure. If height is greater than 10, obviously giraffes are taller, you come to the left. Tigers are shorter, it goes to the right. Now these are very pure. There's no other class in this. So now if during the test time or prediction, if your particular test example is traversing this particular branch and coming here, you can immediately say this is the animal class. It belongs to giraffes class. Similarly over here also, you can see other classes how it has come down to. So that is why you want the sample to be pure, because you can easily predict the class at the end. Okay. So if this is clear and there are no questions, let's again look at a very small example, a very simple marketing strategy example. So if your team has all the customers in your database, then the first question is to ask whether the customer has made, here basically the point over here is to make customer retention. So first question is, has the customer made any purchase in the last 6 months? So based on that, you divide your buyers into recent buyers and others, because your sample will get less and less impure. Then you further ask with they respond to previous email campaign or not. Then this further reduces the impurity. You do this until you come to sufficiently pure groups. Obviously, in this particular case, you saw very pure groups. This is not always the case. Sometimes in many real world examples, you will not get this pure, but you get something close to relatively being pure. So that is also fine. Okay. So why is decision trees very powerful? Because again, going back to our intuition, what are these algorithms doing? These have to form the decision boundaries, right? So decision trees form very good non-linear decision boundaries. So as you can look in this example, if you use a logistic regression, you will never be able to get good accuracy on this example, because logistic regression can only separate linearly separable classes. But decision tree, like you can see, I don't even know what curve to call this, because there is rectangles over here. Then there is again gap in between, another rectangle here, another gap and another big rectangle on the top. So, but this is a decision boundary. Everything that looks purple is one class. Everything that looks yellow is another class. So very good decision boundaries are formed with decision trees. That is why till today, there is a version of decision tree which we'll discuss tomorrow called random forest. Random forests are one of the powerful algorithms for machine learning. So if your task it can be solved with random forest, you don't even have to go to neural networks, because most of the business cases today don't actually need to go to neural networks. Their things can be solved with random forest itself, which is a variation of decision trees. So make sure you understand decision tree very thoroughly by tomorrow, because this will help us understand your random forest. Okay, so now we can look at something called as hyperparameters. If you remember, I told you that there are certain set of parameters called hyperparameters which are not learned through examples, which are not learned during the training process. Like for example, yesterday's logistic regression, you had those weights W, and the weights W were updating right over the period of training. That updation of those weights are something which is called as trainable parameters, because you're during the training time you're updating the weights or you're making the weights more optimal. So those type of parameters are trainable parameters. But there are other certain set of parameters called hyperparameters which do not change during training time. It is a fixed value across training. And what should the value be? That is depending upon the expert domain. So we initially have a bunch of guesses for each of these hyperparameters, like what does this max depth talk? It means that should be the depth of the decision tree. That is one hyperparameter. It can go up to 10 levels, 20 levels, 30 levels. So you need to decide which is good. Again, going deeper is not always optimal. You'll see through examples that there is an optimal value somewhere in between. It's not that you have to always go deep. And then you have minimum sample split. What does this mean? This means that how many samples should I select for each when you are doing that entropy calculation, right? Or the gain calculation. How many samples should I pick from the attribute? That is called as minimum sample split. Then maximum features that you want to calculate at every level, that it defines the maximum features. And also another is maximum leaf nodes you want at the end. So there are a bunch of hyperparameters. How do you select which hyperparameter is good, which hyperparameter is bad? So if you remember, this is where this pipeline comes into picture, which we talked in the first day. So initially you pick some random value, or you guess some random values for all these hyperparameters. Then with those hyperparameters, you train on the train set, and then you do an evaluation on the validation set. So then you get a value for those particular combination of hyperparameters. Next, you take another combination of hyperparameters, repeat this entire process, and again you get a second validation performance value. So like that you do for all the possible hyperparameters which you can think of, and then out of all those you pick which is the best validation value, whichever is giving the best validation value. That particular hyperparameter combination you then take and you evaluate on your test set. That is your final performance metric. So now I hope it is clear where this validation set is coming into play and why it is helpful. So even in your standard neural networks and all, there are a bunch of hyperparameters that you have to take care of. Okay. Any questions in this pipeline? Why are we using validation cycle? What are the hyperparameters and all? Okay, great.
Excuse me.
Yes.
Sir, you have told about the naive Bayes and as well as decision tree. So can we use the continuous data in decision tree?
Yes, you can definitely use continuous data in decision tree. So over there, the calculations will become slightly different. It's not simple calculation like the probabilities. You'll have to again form your Gaussian curves and everything. So like we did for naive Bayes, right, where you formed your Gaussian distributions, you'll have to follow a similar pattern over here also. So it always, for categorical you have a type, for continuous also you have a type. Is that clear?
Yeah, okay, sir. Thank you.
Yeah. Okay. So this is what I had planned for the decision trees and the naive Bayes theory. Now let's go into the code part. I hope the theory is clear. Anything unclear, please ask. Okay, so let's now look into the code part. Before that, I hope you all got the chance to run yesterday's logistic regression code. So maybe I'll just quickly give an overview of what is a Colab notebook and all. So I'm assuming most people are familiar, but still people are new to this field. Colab is a Python notebook which can be used over the internet and without any requirement of any installation on your local system or local machine. So what I mean by that is, if you have a Colab account, which is nothing but a Gmail account, you can run your codes just by accessing, if you have access to your Google Chrome and internet. That's it. You don't have to worry about installing Python in your local system or not. So this is very helpful, especially for people who can't afford good laptops, or for people who are very confused in installing softwares. Because personally, when I started off a few years ago, I there were a lot of issues when I was installing these libraries and I couldn't resolve it. So for all those cases, come to Collab. Best solution you have. Everything is installed. You don't even have to worry about your capability of your local machine. All you need is internet connection and connectivity to a browser. Okay, that being said, so there are a bunch of different libraries which are needed to run your codes. So let's go one by one briefly what these libraries are. So first and most important, like I said on the first class also, scikit-learn, which is shortened as sklearn. Scikit-learn library is very important because it has most of your standard machine learning algorithms existing written in it. So you don't have to worry about writing your algorithm from scratch. You just have to write 1, 2, 3 lines of code, and that's it. Your algorithm is ready to go. So scikit-learn very helpful for not algorithms. But apart from that, there are a lot of standard data sets available. That is what I'm importing over here. A lot of standard data sets are available in scikit-learn, which people usually use to do some test case analysis. Apart from that, there is also something called as the model selection module or library inside scikit-learn, which helps you creating this train test split. So if you remember, we have to create 3 splits, right? Training, validation, and test. And we also have to do stratified training, sampling, where the ratios are maintained across classes for each of the train set, validation set, and test set. All of those again done in one line using this particular function. And these are in next I'm importing the Gaussian naive Bayes. Just like I said, it's already implemented in scikit-learn. You just have to call this class. Then you also have metrics already existing in scikit-learn. You just have to call them, import them using this particular accuracy score. These are the scikit-learn benefits. Now there is 3 other libraries. Pandas library, like I said, it is helpful to load and deal with CSV data. What is a CSV data? CSV data is nothing but this Excel sheet type of a data which you see. It's the official terminology is comma separated values. It basically says that each of these values are comma separated. But don't worry about that. It's just like if you have an Excel type of a data, it is mostly a CSV data. And to load them into your code and all, you use pandas. You can also do some processing and all on that data, which I'll show you today. Then you have a Seaborn library, which is used for visualization. Matplotlib, again, another software which is used for visualization. Okay. Now let's go to the first data which we'll discuss today, which is the iris data. So what is an iris data? Iris data is the most simplest data. It's like ABCD of machine learning, I would say. Any person who's trying to come up with a new algorithm, or for that case, if he's learning a new algorithm, the easiest data he can work on is iris data. Iris data has 4 features. You can see over here. These are plant features basically. There's no images. It's just values. But to show you an example, I took there is a plant on the side, but there are no images. Make sure that it's only the values of these particular features, real values, real number values. So what are these features? Sepals are these particular feature of this plant, which you can see on the bottom, which has white colors. And the width and length of the sepal is the first 2 columns. Petals, you all know what is the petals of a flower. The petal length and petal width of a flower is nothing but the second 2 features, third and fourth features of this particular data. So there is this data set which people have collected, and they said that based on these 4 features, the length, width of sepal and length, width of petal, you can classify 3 different species of a plant, which is Setosa, Verisocolor, and Virginica. So these are the scientific names of these plants. So based on these 4 features, you can classify them into these different classes, 3 classes. Okay, so now let's load the data set itself. So it's very easy to load the data set. Like I said, it's already existing in scikit-learn. All you have to do is datasets.loadIris. It load your dataset into this particular variable iris. Now this iris has 2 attributes, data and target. So you have to just store them in the appropriate variable. Your data will go into X, which is your these 4 attributes. These 4 attributes that will go into your X. Your target, which is your class label, will go into Y. So once you have created X and Y, then you convert this into a data frame. The data frame is nothing but Panda's way of calling an Excel sheet. So you need Excel sheet. You have your entire this right this particular thing. So this particular thing is nothing but a data frame. So that is just a term given in Pandas. So you convert your X into a data frame, and the column names you give, which are the existing column names in the data set, the sepal length, width, petal length, and width. Similarly, your iris in your data frame, the column is which you call as a species that you convert using the target iris.target. So this is what it looks. So once you print this dot head is basically when you use it on the data frame, it prints the first 5 rows in your data frame. So what are the first 5 rows look like? These are the columns: sepal length in centimeters, width in centimeters, all are in centimeters, petal length and petal width, and these are the classes of those particular rows basically. So the first 4 rows are all setosa. Okay, now if I want to learn more about the statistics behind these features, right, it is very important because each feature has their own range, like standard deviation, mean value, then percentile values, and all those things, which is helpful to understand which feature is important, which feature is not. So these are all very important statistics you need to know about a data set. So for that, very simple, you don't have to do anything. Just iris_df.describe. This is your data frame, that data frame which you described in the above code cell. You just do .describe and it will give you the entire statistics of each of the feature. So what are the statistics that you're interested? Sepal length, it will give you what is the count. It's only 150 samples in the data set, so the count is 150. What is the mean of the length? 5.8. What is the standard deviation? What is the minimum value? What is the 25 percentile value, 50 percentile, 70 percentile, and what is the maximum value? It gives the values for all the columns which you have. So very important. Why is it important? Because it also helps you plot something like this. I'm assuming you're familiar with correlation. If you're not, correlation is nothing but if you take 2 columns, right? Just a second. If I take these first 2 columns, if I say that these 2 columns are highly correlated, it means that they're highly dependent on each other. So in opposite way, if I say these first 2 columns are uncorrelated, it means that they don't depend on each other at all. But why is this needed? Maybe it's a question open for you people. Why do you think that my features should be correlated to each other or uncorrelated with each other? What is a good data set? A good data set is when the features are correlated with each other or uncorrelated. Any guesses? You can drop in the Q&A also your answer, or you can unmute and answer. Any guesses? So like I said, a dependency is nothing but correlation. So do you think a data set is good if there are dependency between the features or not? Okay, so the correct answer is they should be uncorrelated. There should not be any dependency. Why? Because let's say in this example they're not, but let's just say all these 4 columns are dependent on each other. Now, if I have all 4 columns of dependence, what is dependence? It usually means that one value is either a summation or a multiplication or a combination of both of the other value. So in that case, instead of 4 columns, I can only use 1 column, because if I have 1 column, I can get all the other 3 columns by just doing some linear change or linear manipulation, either multiplication or summation or both. So I'm not really getting information out of these 4 columns. I'm just getting as much as information as I could get from 1 column. So that is why to get more and more information from your data, it is very important that your features in your data are highly uncorrelated or not dependent on each other. So make sure that whenever you are creating your own data or you get a data, identify which features are correlated and select only one, ignore the other one. So very important to do that check. So for that check, you can do something called as this pairwise plot. So correlated data usually, so none of these are correlated actually, but correlated data usually follow a linear relationship between the, in the graph, in the scatter plot, you can see a simple linear correlation. But in this case, there is not much correlation. The data is kind of spread all around. You see, okay, if you ignore the blue part over here, just see, if you look at these two, this is what a correlated data would look like, very linearly dependent on each other. But since we have points on the bottom also, this is not a correlated value. So you can do that manual check with this. Obviously there are other metrics also for identifying what whether two particular features are correlated or not. I think that's a bit advanced concept, but people interested, you can ask me in after the class. I can tell you, guide you through that. Okay, so once you identify which features are important and everything, next important step is creating your train test split. So for now, we don't need a validation split for Gaussian naive Bayes, because there's not much hyperparameters in this, right? There's actually no hyperparameters. The only hyperparameter I would say is whether to use Gaussian naive Bayes or not. Most of the times, that also by looking at the data you can understand whether to use Gaussian naive Bayes. It's usually used for continuous data. So that's why I'm just creating train and test split and not any validation split. How do I create train test split? You use this function train underscore test underscore split. You send in the x value, the y value. You mention what should be the test size. So this is in fractions. So this is in decimals, but it's basically like 0.3 is 30%. Then you maintain random state, which I'll explain the importance, and then stratify y. This stratifies what we do, explained when I talked about stratify sampling, right? To maintain the class ratios when you are splitting the data set. So that is what it is doing. By writing the stratify y, we do that. Okay, so why is this random state important? So what happens is, in this particular case, maybe it won't affect much, but in more and more algorithms, when we discuss from now on, when a random state is basically related to a random process that runs behind an algorithm. So what could be a random process? Like in logistic regression, right? You saw the weights are initialized with a random value. That's how you start logistic regression. But obviously, how are they initialized matters, because if, for example, somehow I got lucky in initializing my weights good with logistic regression, then I easily converge to the optimal answer. But if I'm unlucky and I initialize my weights in logistic regression with a very bad value, then my convergence will take a lot of time, or it might not converge. So these type of random processes are very much present in all the machine learning and deep learning algorithms. So to control the randomness, we use random state. How do we control that? So for example, if I created an algorithm and I set the random state 42 in all the random processes that are happening in my algorithm, all of them I set a particular state to be 42. It means that whenever this particular state is 42, the sampling from that random process will happen in the same way. It won't be any more random. You're kind of making it deterministic for this particular number 42. Why is this needed? If I do this particular number and I get a accuracy of 92%, 92.36, and if someone else is reproducing my algorithm and if he uses a different random state and doesn't use my random state, he will get an accuracy value which is either less or more, but not my value. So that is why, to maintain this reproducibility between what I am getting and what people outside are reproducing my code, we fix these random states value. So right now we use only one random state for train test split. In the future, you will see that there will be a lot of random values in the algorithm also. Like logistic regression was one simple example. In the future, you will see more and more examples. So always remember, fix your random state. Otherwise, there is no use. No one can reproduce if your random state is not fixed, and the algorithm, we don't know if it's actually working or if it can actually be used everywhere or not. So make sure you fix your random state, and then anyone in the world can reproduce your code. Okay, that being said, let's come back to the naive Bayes algorithm itself. So we have the train test split, and then from there you get your X train, which is your training of a train subset for the features, input features X, then X test, Y train, and Y test. Once you've defined these four values, next important thing is you create an instance of your classifier itself. What is my classifier here? Gaussian naive Bayes. So like I said, you just call this class and this GNB is your instance. Now this is your classifier. To train the model, all you have to do is just dot fit and send the data X train, Y train. And once you, that's it, nothing else. You don't have to worry about calculating the what I said, right? Calculating the mean and the standard deviation for each feature, multiplying all these likelihoods and the prior probability, then calculating the posterior probability. All of this, none of this is needed. Just you do dot fit and everything happens in the background. And now if you want to do predictions, again, you just do gnb dot predict, you send your x test, and for each test example, you'll get a prediction which is stored in this y predict. So y predict is a bunch of different values for corresponding to each x test value. After that, you simply send both of them, your predicted values and your ground truth values, to accuracy score, and it will calculate the accuracy and give you the value. So the model accuracy is 0.91, which is 91%. So like I said, iris is a very simple data set, so easily we could get 91% on this simple data set. We'll discuss probably tomorrow svm, where you can see 100% also for iris data set. So iris is a very small data set, it's just used to make sure that everything is working properly. Now let's come and look into categorical naive Bayes. So for that, usually we don't have much of the categorical data available. So we'll have to kind of convert the continuous values into categories. So that is what we do in this particular data set. So we take a data set called the income data set, which basically predicts the income of adult person given on a bunch of different features, like whether what is the age of the person, what is the working class of a person, what is the education of the person, what is the marital status. All of these different features you take into account, and your final predictor variable, target variable, is income, whether that particular person has income less than 50,000 or greater than 50,000. So as usual, you first import the data. Here we use import the data into data frame pandas.read csv. You load your data, and then you do a dot head to see what are the different features or columns for the first 5 rows in your data frame. Then you do a describe. So in this case, like I said, it's all not numericals, so you'll see a lot of NaN values, which doesn't make sense when it's not a numerical value, a numerical feature. Now you convert. So data drop NA is one thing, which is a pre-processing to be done, because sometimes in most of the real world data you collect, data is noisy, right? So instead of any value, you just have NaN value. So in that case, you just add the statement data dot drop NA, and then it will drop all of those values which are not available, and then it will reduce the number of rows basically. Okay, after that, you need to discretize your continuous features. What are the continuous features? Age is a continuous feature, hours per week is a continuous feature. So you convert them into discrete bins. So how do you make any continuous value into discrete? You basically bin them, right? So for example, if I have a continuous value between 0 to 10, and if I have to make it discrete value with five classes or 5 categories, so I just consider a bin size of 2. Any value between 0 to 2 is class 1, between 2 to 4 is class 2, so and so, so and so. We do that for 5 different classes or categories. So that is what is discretization. That is what you do over here also. So there's this again existing thing available in scikit-learn called k-bins discretizer. You just mention how many bins you want and what is the strategy and encode. This is more specific to this discretizer. So you mention the number of bins and you discretize your features in that way. So now your age and now hours of week will have these values 1, 0. 1 belongs to a particular category which has a particular range. Similarly, hours per week also will have a separate category 1 which has a different type of a range. So once you do that, next is you have to convert your target variable also into a 0 and 1. So there are 2 possibilities, right? If your class is if your value is greater than 50k, it is a 0 class. If it is it's 1 class, otherwise it is 0 class. So it's a binary classification whether the particular income is greater than 50,000 or not. So again, you use the same ordinal encoder as a preprocessor available in scikit-learn. You just do encoder.fit transform to convert this particular last income column. Okay. Then once you pre-process all your data, the process again, everything else remains the same. What is this? You first split your data set. You mention your XY, test size, random state, and your stratify. And then you get all these 4 values. And then you repeat the same process. You first create the instance of your class, categorical naive Bayes. You do dot fit function on this particular data, trained data. Then you do dot predict on the test data to get the predicted Y values. Then you calculate your accuracy of this Y test and Y predict. In this case, you're getting 83.36. Okay. Any doubts? Is everything clear? Okay, great. So then let's move. I'll quickly wrap up this session with the last algorithm, decision trees. So here we implement decision tree. First, I'll just show it on the same iris data set. Like I said, very simple data set, right? So you just load iris over here. And before that, always important, first load necessary import statements. I think everyone is aware of it. So just necessarily load those. After that, you load your iris data set, create your train test split. Here, decision tree is again inbuilt, existing decision tree classifier. Here is the hyperparameter which I'm keeping. Max depth is 3. So I'm making sure that my decision tree does not go beyond the depth of 3. That is one hyperparameter which I chose, and a random state 42. So like I said, right, there are random processes in decision tree. So that is why we are fixing the random state over here. If you have a different random state, you'll see a different accuracy. One good example, when you get this code, right, try to change the random state values and see how the accuracy is varying. So this is all important experiments for you to try. Then only you'll understand how these algorithms work. Okay, so you create an instance of this decision tree classifier, and then you fit that particular classifier on your train data set. Same process. Then you do it prediction on the test data set. You get y predict. You calculate the accuracy. See, decision tree is very strong algorithm, I said, compared to naive Bayes, and it gave 100% accuracy. So that is why it is a very powerful algorithm, because on easy data sets, it easily can give you very good accuracy. But let's go to a little bit harder data set. So this is again a very popular US data set called breast cancer detection data set. So this was created by University of Wisconsin people. So it's a very popular data set because this particular disease detection is very helpful for women. And I think in recent times, they even upgraded the data set again to a larger data set. So it's always good for people who want to enter into biomedical side. Okay, so this data set is also available on sklearn. So you just do data is equal to load breast cancer. So it will load this data set into this variable. Now you convert it into the data frame to see what are all the features. So let's see what are all the features. So there are a bunch of different attributes. All of these attributes basically tells whether if there is any tumor or if there is any abnormality. These are the attributes related to those particular things, like what is the radius of that particular abnormality, texture, perimeter, area, smoothness. So these are all specific to those particular disease diagnosis. So these are all medical terms. So a bunch of different attributes are present. And there are two classes, whether that particular tumor is malignant or benign. So malignant is harmful, benign is not harmful. So based on these features, you have to basically predict whether that particular tumor is harmful or not. So all of these are continuous features. So you calculate, again, all these values, right? Minimum value, maximum value. You can also calculate a bunch of different statistics. And then you look at what is the class ratio. So these are all just statistics which are related to the data set. So you see that more benign classes are present than malignant. So this is again one common thing which you usually find in medical data sets. The number of positive disease data classes are less compared to the number of samples in healthy classes. Obviously, because you have more healthy patients out there than diseased patients, so that is why it becomes hard to collect data sets when which have more positive diseases. But there's another technique to overcome that. Again, we'll discuss that later if you're interested. So this is another plot which you can do across different features. Again, this is not a correlated plot because the plot is kind of scattered everywhere. Correlated plots, you can clearly see when they're correlated. So all of the features usually in this are also not correlated because these are these are data sets which have been pre-processed and made very well. Okay, so after you load the data set, here I'll show you how you can create your, first we'll create a simple test train, and then I'll show you how you can create your validation set and that entire validation pipeline also. First, let's do a simple train test pipeline where you first split your data set using the train test split. You create your decision tree classifier based on your max depth and random state. You fit it to your value, you predict it, and then you calculate your accuracy score. There is also something called as classification report, which is again present in scikit-learn. So this will give us a bunch of these other values, which is your precision, recall, F1 score. You remember the other evaluation metrics. Why did I use it over here? Like I said, these metrics are very important when there is imbalance. So there is imbalance in classes, and also the misclassification cost is high. So if I misclassify someone who's having the cancer and saying that they don't have, it's a very high cost. The cost is life, right? So that is why you need to use the other metrics, not just accuracy, because accuracy is giving very high values, but other metrics will give a relatively lower values, and then it means that your model is not very good. So just make sure that you always get those values correctly. Okay, then let's do the validation, training, validation and test pipeline for decision tree, because here we have hyperparameters. So how do we create these splits first? So here you first split your entire data set into two parts. Here I'm calling temp and test. This test is your final test. Now this temporary you again split into two more parts, where it will become the train and validation. Very simple logic. You don't have to think much. Take your entire data set, split it into two parts. The test will be the final test. The train, which is coming after the first step, is your temporary. Take the temporary part, send it into another train test split, and again you split it into two parts, and here you get train and validation. So now you have a bunch of different depth values going from 1 to 11. So you write a small for loop, which basically uses each of these depth values one at a time. So for the first value, this for loop contains all the 1 to 11. So for each depth value, you create a classifier, decision tree classifier. You fit it on the training data set. Then you calculate the score on the validation set. And based on the score, if the score is better than all the scores that was till now, you just replace that particular depth value to be the best depth value. If it's not, then you just ignore. So in this small for loop, you're basically selecting which is the best depth that will give you the highest validation score. So once you are done with that, you pick that particular depth value, and then you again create your decision tree classifier, train it on your final combined train and validation data set, and then you test it on your test data set. So this is how it look. So you have 10 different depth values. All of them have their corresponding validation score, and you see the best depth is with depth 3 with a validation of 92.9, and your final test score is 94.7. Okay, is this clear, or any questions in hyperparameter tuning? Because this is a very simple form of hyperparameter tuning. You'll do in a much more advanced forms for other algorithms, but the idea remains the same. So if you have any doubts in this hyperparameter tuning, please let me know. I can discuss it one more time. Okay, great. So if there are no doubts in this, I think this is what I wanted to discuss for today's, and I think there's also time. Okay, yeah, we've reached the time. So yeah, thank you all for listening. Any questions, I'm happy to answer. Please, you can either post your questions in Q&A or you can unmute and ask. But this is what I wanted to discuss. Yeah, please tell me.
Sir,
Yeah.
sir, can you please send these code samples so that we will try
Yeah, sure. I'll
with the
send you.
data?
Yeah, data is all available anyways in the code. You don't worry about that. So I'll send the code samples and also the lectures, both.
Data set also, sir.
Yeah, data sets are available. So it's already, like I said, it's existing in scikit-learn. You don't have to download it.
Okay, sir. Okay.
Yeah. Okay. I think, ma'am, there are no further questions. Then I think we can end the session.
Okay, sir. So thank you, sir. The day 3 of faculty development program was full of knowledge, and the session was very informative, sir. So the explanations given by the Aveen Dayal sir is highly informative. So sir emphasized on the topics naive Bayes and the decision trees, and mentioned the importance of algorithms by explaining the real-time applications, decision boundary and hyperparameters, and the programming part using the Colab also. Thank you, sir. Thank you very much. And
Yeah.
dear participants, so tomorrow sharp 7 p.m. join the session, and attendance is mandatory for the FDP program.